like I'll record it. It's fine. Okay. So theoretically, it's recording right now.
In theory.
I get
Okay.
it theoretically. That's fine.
That's the first joke of the day. Okay. Okay. So welcome.
Hey guys, welcome to Theory Thing.
You want to give the lecture on?
Sorry.
Okay, that's fine. Okay, yeah. So this is Theory Thing. Today we are going to be talking about the sensitivity conjecture. I'm just going to put a link to the paper in the chat in case anyone wants to follow along with the math. Like have it be able to scroll back and forth. If I can find the chat.
You're just like a regular professor.
Okay, so the link is in the chat. Okay, so yeah, so this is a pretty famous result from last year. This guy called Huang from Emory, I think he proved it, and it was a pretty famous conjecture in this field of theory. And it had been unsolved for many years. I don't actually know. It's 1988? No, earlier than that. I don't know the history exactly, but it was unsolved for a while. Mark could probably tell you more about that. And then he solved it in like a very short paper, and it's remarkably short. The paper itself is like 6 pages, of which 1 page is references. First couple of pages are introduction. The proof of the theorem itself is 2 pages tops, and it's all very simple math, which is quite remarkable for something that's been unsolved for a while. So yeah, okay, so we'll just get into it. Okay, so what is the sensitivity conjecture, right? Okay, so first you need some definitions, obviously. So the sensitivity, so we're talking about functions, right? This is a joke that Marth likes to make because he's not original, is that whenever a theory person exists, he just writes down a function from he or she just writes down a function from 0, 1 to the n to 0, 1. It's just a classic theory person thing to do. It's just a Boolean valued function that accepts some bit string and outputs another bit string. So like, for example, a function could be like, and all of the bits, which is only your outputs 1 if everything is 1, otherwise 0. Right, so this is just some random Boolean function, and you define the sensitivity of a function and an input to be, this is harder to write on this than it looks. Yeah, so the sensitivity of a function on an input, the local sensitivity, is defined to be the number of indices that you could flip in the input such that the output would change. All right, so for example, suppose you had the function be like, I don't know, and of everything, right? So f is and it's like n equals 4 or 3. Let's just do 3. So then f is 1 if x is 1, 1, 1, and 0 otherwise, right? And I'll obviously feel free to like just unmute yourself and ask questions or clarifications or point out something I do wrong whenever. So yeah, so the sensitivity of the function, of this function on the input, let's say 1, 1, 1, would be the number of indices within the input that you could flip such that the output changes. So what is the sensitivity here? Anyone?
1, baby, here we go.
1?
Yes, right.
It's 3 because you could change any of them, and then.
Right.
But you only have to change 1, I thought.
No,
Right,
but
it's
like
the number of
the number of things you could change.
Oh, so we consider each one individually then. So
yeah.
So we could change each of them. If we change any of the 3, then the output changes.
Yeah, exactly. So you could
Okay,
change
then
the
3,
first
baby.
one. Yeah, so you could change the first one to 0, and that would change it. Yeah. So obviously for this it's 3. For another input, I don't know, what is it?
Just 1. There's only 1 input you can change.
Yeah, just 1. You have to change the 0 to a 1, otherwise it just stays at 0. And yeah, I don't know, something like this would just be 0, right? Because you can't change a single index and make the output change. So this is the sensitivity. It's called the local sensitivity, I think, where it takes in a function and an input. And the sensitivity of the function itself is defined as the max over all x of s of fx. Right? So you look at all the possible inputs to your function, and you calculate the sensitivity, and the max of all of those numbers that you calculate is the sensitivity of the function itself. So for this one, I think it's, so for the and of 3 things, I think it's probably just 3. Yeah, that's probably right? Because everything else, if it originally outputs to 0, then you're going to have to switch things to 0. So it's going to be either 1 or 0. And yeah, so for this function, it's 3. Yeah, you could. Is anyone unclear on the definition of sensitivity?
So you can't have a sensitivity more than like n, right?
No, I mean, because it's a count of the indices.
Right. So you can't.
That it's between like 0 and n.
Okay. So it's 3
Okay.
because that's the n. All right.
Yeah. Okay. Yeah. That's a better way of seeing it.
Okay.
Yeah. So that's the sensitivity. And there's this other notion of sensitivity called the block sensitivity, and it's a little less, intuitive, let's say. So the block sensitivity is similarly defined in two steps. So the block sensitivity of f of a function and an input is defined as follows, right? So you take the indices 1 through n, and you split them into some disjoint blocks, b1, b2, bk, right? Where each of these blocks are subsets of, this. All right. And you so you partition, or not necessarily partition, you don't have to partition them, but you just take out disjoint subsets of this big set. And the block sensitivity is defined as the maximum number of these blocks such that flipping everything within those indices flips the output of the function. Okay, so that's a lot of words. So I'll just like go through a tiny example. So let's just do the and function again, but for like n equals 5, right? So let's say, so your set is 1, 2, 3, 4, 5, and your blocks could be, I don't know. I guess this is the wrong notion. You don't necessarily pick the blocks first and then do it. But so basically the question is, you have to split this set up into some blocks such that the max, such that if you take each block, flipping all of those indices in your input flips the output, right? I don't know if and is the best. Okay, let's.
Yeah, because each thing is just like each block is just the individual element for and, right?
Yeah, let's just do an example, I guess. I don't know. So block sensitivity of this function with I don't know, 1, 0, 1, 0, 0. Right, what would this be for f being the and function? Anyone?
So are we given like blocks, or do we have to choose from like the max of all the blocks?
You can construct your blocks however you want, but you want them, so you want to come up with some optimal splitting of these blocks such that you get like the maximum number of them.
So wouldn't it be, you want a block of like indices 2, 4, and 5, and that would be like,
Okay,
But you want
they have to
3
be, like,
blocks,
in
right?
order.
well, the blocks can be anything, they're just subsets. But so you're saying take one of the blocks to be 2, 4, 5. Yeah, and that's it, no other blocks, right? Jack?
Well, to maximize block count, you have to take like 1 as 1 and then 1 as 3, right?
Well, no, because flipping those wouldn't change the output.
Yeah. Okay.
So they don't count. So okay. So
Oh,
this is one choice of the blocks you could pick. But if you flip everything in here, then your input becomes 1, 1, 1, 1, 1, which does in fact change the output of the function.
Mhm.
But this is not optimal, right? Because because you could just you could have picked the blocks to be instead. Actually, is that this is optimal. This is probably
Yeah.
optimal.
Okay.
Yeah. Okay. Yeah. I don't know what I was thinking, but yeah. So this is this correct though? Can someone confirm? I didn't actually go over examples
I can
before.
confirm.
before
I
this.
don't know what
You
you're
were the
talking
teacher.
about. Yeah, you confirm.
I don't know. I didn't go through examples. I just read the paper, man.
All right. Well, let's see.
Yeah, this seems right to me. Okay, so can anyone tell me why this is true? Oh yeah, I forgot to give the actual definition of the block sensitivity. So yeah, the block sensitivity similarly defined of the function is max over the inputs of block sensitivity of f of and x, right? Similarly defined. You look at
Sure.
all the things. So can someone tell me why this would be true?
So you just make each of your blocks include each of the sensitive bits in your max x or whatever. So like each block that you like, if you include a sensitive bit, then like changing that will change the output.
Like the
Well,
set of blocks includes like the set of like single bits that you can change. So
okay,
like
that's more accurate. So Aditya, what you were saying, not quite, because just because you have a sensitive bit in your block, you could have other bits that flipping them could
Okay.
reflip your input, reflip
see.
your output.
Yeah.
So then it would. So yeah. So basically, I mean, I think this is what Jack was saying, but you take each bi to just be the set I, right? And you only count the sets. Obviously, not all of these are gonna work, but the ones that do are gonna be exactly the ones that count towards S of f, right? And so this is an example, and then you can probably improve. So it's greater than or equal to the. So yeah, so this is just sanity check whether we understand definition. Does everyone understand kind of what's going on here? Does anyone not understand kind of what's going on here? Okay, so the sensitivity conjecture is sensitivity conjecture just states that does there exist some constant such that block sensitivity of f is is polynomially related to the sensitivity, right? So this c could be whatever. Like we don't like this is like a theory that like it could be 4,985, or it could be 0.1. But the point is you just want them to be polynomially related. And this is important because there's a lot of other senses of complexity. So you can kind of see how this is kind of just measuring some sort of, both these sensitivity measures are kind of measuring some sort of, some properties of your functions that may or may not be super intuitive, right? So like the sensitivity is, how susceptible you are to changing your output, kind of in some sense. And the block sensitivity is a less intuitive generalization of that, maybe. And there's a lot of other complexity measures. I'm just reading from the paper. They talk about decision tree complexity, certificate complexity, quantum and randomized query complexity, and the degree of Boolean function. Not all of those of which I know what they are. But the degree of a Boolean function, I think what they mean by that is just if you write out, you can write out each Boolean function as some polynomial, right? Like y'all are aware of this. Like if you just have like and of two variables, like x and, is that and? I don't even know. X and y, is that and? Yeah,
Yes.
okay. Then you can write this as I don't know. What can you write it as a polynomial?
Mart says x,
times
y.
X times y, yeah. Because they both have to be 1, right?
Sure.
And you can do this more generally by just writing out the truth table, being like x, y.
Mart's a genius.
I agree. We did this in architecture, I think, where you write out all the like you write it out as like an and of ors, and then you can write out each and as like a multiplication or an
And
or
each
of
or
ands.
is
I don't remember, but you kind of understand the concept of representing all these functions as polynomials, and so the degree of that is another complexity measure. And the point is that the block sensitivity here is known to be polynomially related to all of these other measures, but the sensitivity, this just the regular sensitivity, is not known to be, before this paper, was not known to be polynomially related to all of these, which was kind of unsatisfying to people because it seemed like it should be. And so this conjecture, it's been around for a while, and people didn't know how to get at it. The bounds that they had before this paper were Vs of f is O of e to the s of f times square root of s of f, which, as you can see, I may have a fire. Hold on. Okay.
Quality meme. You can temporarily pause the recording too, if that helps.
Hold on. How do you pause recording?
You click the record button.
Okay. Yeah, what was I saying? Does anyone remember what I was saying?
You were saying what you just wrote on the thing.
That's a good point. Okay,
Oh,
yeah. So
is that a recent bound?
Yeah. This is the I think the best known previous bound. Yeah, the best upper bound. This is the best upper bound, and this, you can clearly see this is not exponential. This is not polynomial. This is exponential, which is much worse. Which is why they wanted to improve it, and this guy did in a pretty legendary paper. And okay, how are we on time? Okay. Okay, so the kind of key previous result, I think, that they relied on to prove this, or he, I guess, is just one guy, is this thing called Gaussman and lineal. Well, I mean, that's the names of the people that prove the theorem, but it's their theorem. So the theorem basically says this, all right. Okay, so these two statements, so the theorem is this. Okay, so it says that these two sentences that I'm about to write are equivalent, which means like they imply each other. There's one is true, the other is well. For a monotone function h from the naturals to the reals. Okay, so I will go over any required vocabulary in a bit. Let me just write this down. For any induced subgraph h of q to the n, there's a lot of vocab in this. Okay, v of h is not 2 to the n minus 1. Why am I just writing this down verbatim? I should have planned this better. It's greater than or equal to h of n. And for any Boolean function f, that's not an f, f, s of f is greater than or equal to h of the degree of f. Okay, so what does this mean? Okay, an induced subgraph. Does everyone know what an induced subgraph is? I'll just go over it anyway. So if you have a graph is a bunch of vertices, and some of them are connected by edges. Some pairs are connected by edges. An induced subgraph is just where you pick some of the vertices and you take all the edges that make sense to take. which means just the edges that have vertices, both of their endpoints in that set of vertices, right? Like if you had, obviously you won't take edges that have endpoints outside that set of vertices because it's like, you don't know that they exist, so why would you do that? So that's what an induced subgraph is. Q to the n is what the hypercube, like the n-dimensional cube graph, right? So it's the generalization of the cube, right? So first you have like the line, I guess, and then the square, and then you have your cube, right, and so on. So this is the hypercube. The way it's defined is you just have all the vertices in 0, 1 to the n. I guess I don't actually know how it's defined, but this is one way of defining it. So 0, 1 to the n, and these are the vertices, and v1 and v and w are connected if like
Only one of them is different.
yeah, like if the Hamming distance of the two is 1. So like if only one of their bits is different. Right? So you can kind of see that here where you have like 0, 1, 1, 1, 1, 0, and 0, 0. 0, 0, and 1, 1 are the only ones that don't have one bit, or I guess, and the two diagonals. And you can see they both have both their bits flipped. So the only ones that are edges are the ones that only have one bit flipped. So that's the hypercube graph. So this theorem is saying is okay, and v of h. What is v of h?
Is it the number of vertices?
Yes, that probably is correct. V of h is the number of vertices, and this capital gamma, is that a capital gamma? I don't know. I think it's a capital gamma. The capital gamma of h is I don't know if it's standard notation. It's defined here. It's the max of the delta of h and delta of un minus h. And delta of h is max degree of h. Does this make sense? So you have some subset of vertices h, you look at the max degree of that, and then you look at all the other vertices, right, and the induced graph on that, and you look at the max degree of that, and you max these two things, right? So you take the one graph and the other graph, and you look at the maximum of the two max degrees, and that's gamma of h. So yeah, going back to this statement here. So what this is saying is for any induced subgraph h, so like if you take any subset of the vertices h, where the size of the vertex set is not 2 to the n minus 1, right? And what does that mean? That if the size of the vertex set is 2 to the n minus 1, that means it has exactly half the vertices, right? And we'll talk about that later, about what happens when that happens. But so if you have any subgraph that has like not exactly half the vertices, and you have that gamma of h is larger than h of n, that's the first sentence, right? So is that clear? Oh, wait, I phrased that wrong, but so you're trying to prove equivalence of two sentences, right? So the first sentence is just that for all induced subgraphs, this equation is held, right? Now this isn't going to be true for every function h, right? But if a given function h fails this statement, then it will fail this statement, is what this theorem is saying. All right. Okay. And now the second sentence is for any Boolean function f, the sensitivity of f is larger than h of the degree of f. The degree of f. Sorry, the degree of f is what we talked about earlier. I think the degree as a function, which is one of those complexity measures that is polynomially related to the block sensitivity. So as a corollary of this, Okay, so let me just ask this as a question, just because I feel like I'm kind of losing some people, unless I don't know. It's hard to tell if I'm losing people when I can't hear anyone's voice. It's kind of sad. I'm just gonna erase all of this. Okay, so if you could prove that this is true, then what would you have? What could you say?
That the sensitivity is greater than or equal to the square root of the degree?
Yeah. So if this is true, then this implies that the sensitivity of f is greater than or equal to square root of the degree of f.
Wait, can you remind me what degree is?
The degree is, so like if you write out the polynomial of the function, remember where we wrote and as like the product?
Right.
Then the degree of that.
So the degree of that polynomial. Okay,
yeah,
sure.
is the degree. It's just one of those complexity measures that like one of those things that's all polynomial. I can't say. Can anyone? Is it okay? Whatever. Polynomially related. It's one of those things that's all related to the other thing.
Okay,
And
sure.
and there's another prior work that gives that the block sensitivity is less than or equal to 2 times the degree squared, which would then mean, this is just prior work. So then this would just mean that the sensitivity of f is greater than or equal to sensitivity of 4, the fourth. Yeah, that seems to be right. Wait, no. What did I do wrong? Oh yeah, no. Okay, so if you fourth power this, yeah, that's true, right? Yeah, because if you square this equation, you get s squared of f, or fourth power it, then s to the fourth of f is greater than or equal to the degree squared of f, which is like greater than or equal to the block sensitivity over f over 2. Yeah. Oh, okay. Yeah, this makes sense. The 2 goes away. That why would you mention this result if you're just going to talk about another one later? I don't know, man. Okay. Yeah, this is clear. So if you had this thing right here, you would prove the sensitivity conjecture. Because remember, the sensitivity conjecture was just this, and then we'd have that C is 4, and then we'd be done. And guess what this paper does?
Exactly that.
Yeah, wow, what a concept. So the main result, well, okay, the main result is, I guess, yeah, but the main theorem is that this statement is true here. And why that is true is what the proof is about. So we'll get into that now. And okay, because can anyone tell me why they had this? Well, okay, this is not necessarily why they had that. The why they had it is because it wouldn't work otherwise. But why does this requirement make sense? What would happen if you could have exactly half the vertices?
You could have your induced subgraph be the whole. No, that's not an issue.
You want the size of your vertices to be like half the vertices, right? Not everything. Can you think of some example, like looking at or I erased the hypercubes, but can you picture a hypercube in your head as one does?
You could take like for the square case, you could take the diagonally opposite ones, and then there are no edges in the middle, right?
Right. How would you generalize that? Like for the cube, what would you do?
Can you do the same thing?
Is it antipodal points or like?
I mean, there's many sets of antipodal points. How do you match them?
Yeah.
But you can't take 4 vertices from a cube such that there are no edges between them.
Can you not?
Can you? Hold on.
Think about how we define the hypercube graph, where two vertices are connected.
Oh yeah, you could do it recursively. So like you do the
You
top
always-
part is like the square, and then you could like flip it and do the.
Oh, right.
You
Flip
don't
right
have
there,
to
and
give an
then-
algorithm.
But like it makes sense. It's fine.
No, okay, yeah. Wait, what were you saying? I just stopped paying attention when you said.
I mean,
recursive.
like for the cube, when you're doing the square, like you can do like you have like a pair of antipodal points, and then you
Yeah,
like,
yeah,
rotate
okay,
it
yeah.
and do that, and then you come up with some intuition for doing that in like 3-dimensional and 4-dimensional.
Sure. Well, another way of seeing what the hypercube graph is just that you take two copies of the lower dimensional one and
Yeah.
match pairs and
Right,
connect them. So yeah, that's possible. It's not super immediate that you could do that for higher dimensions. Maybe it is, but
Yeah.
a simple way of seeing this is you look at all the vertices and you look at you partition them into the ones that have even sum of digits and odd sum of digits.
So bipartite.
So you can split the graph in half. That's
Yeah,
it.
and then you can
That's
make
not
the
bad.
capital gamma be 0, right?
Yeah. Well, like, does everyone see why the capital gamma would be 0?
Because
There are no induced edges.
Any edge switches
Yeah.
parities. So
Yeah. So an edge goes between an even vertex and an odd vertex because exactly one bit gets flipped, right? So yeah, that's why the 2 to the n minus 1 thing doesn't work. So basically, what the theorem 1.1 of this paper states that if you have for any induced, let's just say theorem 1.1, for any induced subgraph h of q to the n, where, or I think, oh yeah, okay, let me just, oh yeah, okay, where this is 2 to the n minus 1 plus 1, then this. Oh my goodness. Why are smoke detectors like, does this happen to everyone, or is this just me? Because this happens like every 5 months wherever I live. It's crazy.
Is your mom cooking or
My
something?
smoke detector
No.
doesn't have
I
batteries.
tend
It's like
not to
4
burn my
o'clock.
house down personally.
No, it's
That's
when
just
they run out of
right.
battery, they
That's
just like
right.
decide to
Yeah, no.
proclaim fire. This is,
No, but they
I
don't
think
do that,
we-
right? When they do
I
low
think
battery,
we
they usually just have the
temporarily
beat. Yeah.
disconnected ours.
Yeah, I
that's
don't know.
fine.
No, like
Legend.
you remove the battery and then they can't beep.
Yeah, exactly.
that's probably illegal, but sure.
Wait, it's not illegal. I mean, it's
Mine
It's
still
just in your
beep
own
when I
house,
remove the
yeah.
battery.
Yeah.
Wait, unplug the cable thing.
Yeah,
This
that's
is a
what I do.
Friends episode. But
Oh
anyway.
yeah, good times.
Yeah. Yeah.
Wait, is
Yeah,
the
so-
delta the max degree?
Yes.
Oh, okay. Uh-huh.
Hey, Brian.
Alex.
So like if you think about what this theorem is saying is we just showed that if h has 2 to the n minus 1 vertices, then it's possible for delta of h to be 0. What this is saying is immediately, even if you add one more vertex in there, immediately the max degree jumps up to root n, which is, interesting, I guess. Okay, so this is the theorem, and they prove it using three lemmas, right? And we'll go over them now. The first lemma is what is called Cauchy's interlace theorem. I think everyone here knows what eigenvalues are, correct? Does anyone not know what eigenvalues are? I think everyone here has taken Linalov/Diffie-Q. Benefits of knowing everyone at your theory thing. But yeah, so okay, everyone knows what eigenvalues are. So Cauchy's interlace theorem is the following, right? So if you have some matrix A, which is I don't know, n by n, and B is a principal submatrix in I don't know, Rm m by m. And a principal submatrix is just when you take the matrix and delete some rows and columns, corresponding rows and columns, right? So like, is it corresponding rows and columns? I think it is corresponding rows and columns. Yeah, the same set of rows and columns. Yeah, so like if you delete the first row, then you also delete the first column, right? So you delete things that look like this, and like possibly multiple of them. So B is a principal submatrix of A. Then okay, let me just write this down because it has a fancy-ish name. Cauchy's interlacing theorem. Okay, so and you look at the eigenvalues of A. Lambda 1 greater than or equal to lambda 2 greater than or equal to lambda lambda n. And you look at the eigenvalues of B, mu1 greater than or equal to mu2 and mu m. Then for all bounds here are a little annoying. Lambda I greater than or equal to mu I is greater than or equal to lambda I plus n minus m. Yeah. Which is a little obscure because it's not immediately clear what the heck is going on here. It's a little more intuitive if you imagine m to be n minus 1, right? So you just deleted one row and column of A. B is just one dimension smaller in one size smaller in both directions. So B has one fewer eigenvalue, right? So what this is saying is that if you plug in m equals n minus 1, lambda I is greater than or equal to mu I is greater than or equal to lambda I plus 1. Or sorry, I minus 1. Right? Which if you write the whole inequality chain out here, like if you combine that with this, you just get that lambda 1 is greater than or equal to mu 1 is greater than or equal to lambda 2 is greater than or equal to mu 2 is greater than or equal to da da da. Right?
So it's plus 1 then?
Oh yes, okay, fine, plus 1.
Okay.
Yeah, okay, yeah, I did the math wrong. Negative 1 is positive 1. Right. So this makes sense. So the name interlacing theorem also kind of helps. Right. So the eigenvalues just kind of like interlace themselves. When you have m which is smaller than n minus 1, you just basically get that if you write out the lambdas, you have lambda 1, lambda 2, lambda 3, lambda 4, and so on. Then the mu1 is between like some window of the eigenvalues, and mu2 is within some other window of the eigenvalues, and so on. Right? The proof of this, I don't know. It's probably complicated. I don't actually know. I didn't look at it, but they just cite some other paper, so we're not going to go into that. Second lemma that they use. This is just something to keep in mind. They're going to use this as a tool later. Second lemma that they use is a little more concrete. That they actually prove here. So defines these matrices, right, recursively. A1 is 0, 1, 1, 0. AN is AN minus 1, I, negative an minus 1. Right? So these matrices are just put in as blocks. I is the identity. So if it's the dilemma is that for these matrices, an has eigenvalues root n and negative root n of multiplicity 2 to the n minus 1 each. Okay. Proof. Okay, who wants to take a crack at this? How, or just like, and how would you try to prove something like this?
We'd start with the base case and prove that that one has the eigenvalues, and then we'd like induct. And if we go one size bigger, then
Yeah, exactly, right. So induction seems like it's probably going to work because it's like, you know, recursively defined, lends itself naturally to induction. But like, what exactly do you want to prove here? So like, to prove directly that the eigenvalues are root n, negative root n, I don't know. There might be a way of doing that. Can anyone think of like a simple way of showing that the eigenvalues are either root n or negative root n? Maybe. So would this be good?
that'd work, right?
Yeah, so this is basically all you need, right? Because, well, that's how it works. Like, so if you have, so to prove that this implies that the eigenvalues are root n and negative root n, you can just take some vector, some arbitrary eigenvector, and this is equal to like lambda vn, and then I don't know, you can look at an squared vn. This would be lambda squared vn, which is equal to n squared I squared vn, which is n squared vn. Or sorry, not n squared I squared, just ni vn, which is n vn, which means lambda squared is n, which is what you have. I don't think I needed to show that, but anyways. So if you prove this inductively, you'd be done, and that's actually not super hard to do. You can multiply matrices in blocks is the key here. If you just take an minus 1 I negative an minus 1 and square that, you get, the first thing is an minus 1 squared plus I. This thing becomes 0. Well, we want it to be 0. This is also 0. This is also an minus 1 squared plus I. And, yeah, which is then just, so by inductive hypothesis, we knew that this was n minus 1 I. So we just get that this is ni 0 0 ni, or well, this is, and that's just it, right? Where these i's refer to different dimensioned i's, but you get the point. Yeah, does anyone have any ideas on proving the multiplicity part? This proves that the eigenvalues have to be root n and negative root n. How do you prove that they're half of them are root n, half of them are negative root n? What are some facts, random facts about eigenvalues?
Wait, so maybe make some attempt to construct the like structure of the eigenvalues and like show that there are 2 to the n minus 1 of them, possibly.
You mean construct some vectors? Like
Yeah.
eigenvectors?
Yeah.
Maybe. That's a little less elegant
Okay, yeah.
than, but sure, yeah, I mean, maybe that would work. And do you know any other facts about eigenvalues? It's probably like the third fact that you might care to cite.
Brian said it in chat.
What did he say?
Trace of matrix
Yeah.
is sum of eigen.
Right, exactly. So, oh, sorry, I don't have the chat open, which I should probably change. I'm missing all of Brian's amazing comments.
I don't think they're that amazing.
Why? What? If y'all had questions, just ask me. Hello. Why didn't he just write Gauss millennial theorem? Was there? Oh my, that's not a question. Stop distract. Okay, so yeah, trace. As you can see, the trace is 0. How can you see that? Well, inductively, right? So the trace of the first one is obviously 0 because it's 0, 0, and the trace, like the diagonal elements, just are always going to be 0. You can see that from the construction. You just take the matrix and put it along the diagonals. So the sum of the eigenvalues is 0 because the sum of the eigenvalues is the trace. So then you have like some a root n plus minus b root n is 0, which just has to be, they just have to be half and half. And so a plus b equals 2 to the n, which proves the lemma. Okay, last lemma, which is probably the most involved one, but it's actually not involved at all, which just speaks to how simple this proof is. Okay, so last lemma. Let me just remind myself what this is. Okay, yeah. So if you have, okay, so H is graph. Why did I say that? H is a graph, right? And A is matrix with entries in 1, 0, -1, such that, Aij is not 0 if and only if the vertices I and j in H. I did both the capital and the lowercase h right there. That's impressive. If vertices I and j and H are connected. Right? So this is this is almost the adjacency matrix, except that you can also have a -1 in the entry, right? Like it doesn't just have to be a 1. It could be a 1 or a -1. The point is that if the vertices are not connected, then no, I haven't, Anj, please. Okay. Yeah, you have to have a 0 if you're not connected. Otherwise, you can have a 1 or a -1. If this is true, then the max degree of H is greater than or equal to λ1 of A. Okay, so λ1 is the largest eigenvalue of A. Delta is the max degree. Everyone understands the statement. It's pretty pretty simple. Does anyone not understand it? Is anyone lost?
So you can assign like 1 and -1 arbitrarily, right?
Yeah.
Okay.
Okay. So so the proof. So let V1 be eigenvector with eigenvector. I have to write eigenvector with eigenvalue λ1. You have that A V1 or okay. λ1 V1 is a V1, right? This is just by definition of eigenvalue, is Okay, okay, here, I have to add some more notation. My bad. So let's just call this vector V. Let's V be the vector that has eigenvalue lambda 1. And let V1 be the coordinate of largest absolute value in V. Okay, so like it's a negative 4,000. Everything else is just like 100 something. I don't know. It's the largest
Like
absolute value.
Like the index or like the.
Yeah, like the first one, like V1, arbitrarily. It doesn't really matter.
Okay.
You can just it's just for bookkeeping. You just need to keep track of that index.
Okay.
Just V1 doesn't matter. So then you have lambda 1 V1 or lambda 1 V. Yeah, lambda 1 V1 is a V is the first index, correct? Because lambda 1 V is a V, and then you look at the first indices of both of those vectors. Yeah? Okay, this is equal to, by definition, the sum from j equals 1 to n of a 1j, yeah, 1j v1. This is just the matrix multiplication written out. And since we know that a1j is going to be 0 if v1 is not connected to, if 1 is not connected to j, we can rewrite this as where this notation just means j is a neighbor of 1. Right? Okay, and this is less than or equal to, or sorry, yeah, this is equal to, and this is less than or equal to, did I miss any inequalities here? No, yeah. This is less than or equal to the sum, j is 1, a1j v1. This is by triangle inequality. Yeah? And can anyone tell me the last step here?
Which is bound by the max degree, because at most you just have like all the aij are 1. Or wait, or is it degree of h times v1?
Yeah, it's the degree of h times v1, because
Yeah.
I mean, this v1 is not, doesn't have to be in the sum, right? It could just be out here.
Yeah.
And then you just have the sum, and that's each thing in the, each j that is a neighbor of 1 is going to contribute a 1 to this sum because it's absolute value. So you're just going to have something that is less than the max degree. So this is less than or equal to max degree of h times v1. And yeah, this is just, okay, theorem, lemma proved. Now we are basically just done. Now we just have to put these lemmas together. Okay. Okay. So now what they say is that if you consider these sequences of matrices, the sequence of matrices an, you, first of all, it's obviously all the entries are 1, -1, and 0, right? So they satisfy the constraints of our previous lemma, so which just needed them to have entries in 1, -1, and 0. And it's not, okay, it's this, you can see how this is just the adjacency matrix of the hypercube. Right? So the way to see that is this is the adjacency matrix of this graph, right? Is that clear? Because you have the two vertices, one is connected to the other is connected to the first, right? And this step right here, remember when I talked about the recursive definition where you take each lower dimensional hypercube, have 2 copies of them, and just connect corresponding pairs? So this, the identity matrices here, I think, correspond to the, yeah. So this corresponds to the one of the lower dimensional hypercubes. This corresponds to the other. The negative doesn't matter because we don't care about plus or minus ones here. And the i's here correspond to those matchings between the two, right? So for example, you'd be taking two of these, and those would be your an minus ones, and then you connect them, which is the identity part. You can think about that if it's not clear to you. Maybe you just write it out for a couple of small values, like the square and the cube, and see why that's true. So so yeah, so this an, if you with absolute values, is the adjacency matrix of Qn, right? Yeah. So basically this is just trying to show that everything is satisfied for lemma 2.3 to be applied. Okay, so now what you do is you want to prove this theorem right up here. If we've forgotten what theorem we're proving, theorem 1.1. This is what we're trying to prove. Is that given any h, which is a subgraph of Qn, then this is true. Now, does anyone have any connections to make with induced subgraphs and something else that we've talked about?
The Cauchy interlace theorem.
Right. Well, in particular, the principal submatrix, right?
Yes.
So if you take some vertices H, then the principal submatrix is just is just the similar thing for the induced subgraph, right? So what you get is that if you apply theorems, okay, so hold on, let me read this a second. Yeah, so if you have some for some H, subgraph H of 2 to the n minus 1 plus 1 vertices, you have let AH be the principal submatrix of AN, or AN corresponding to those vertices, right? Then we know by lemma 2.3 that this is true. Yeah? Now, from the second lemma, we have that the eigenvalues of AN are root n, root n, root n, negative root n, negative root n, negative root n, right? And we know by the interlacing theorem that the largest eigenvalue of AH has to be somewhere between, if you do the math, here and here. All right. So in particular, so you have this has 2 to the n minus 1 vertices. So lambda 1 is greater than or equal to mu 1 is greater than or equal to lambda 1 plus 2 to the n minus 2 to the n minus 1 plus 1, which is, or sorry, plus 1, which is lambda 2 to the n minus 1. And you know that lambda 1 is root n is lambda 2 to the n minus 1, which means that the largest eigenvalue of AH is just root n, right? Which just gives you what you want. That gives you the max degree is greater than or equal to root n. And you're done.
Fancy.
right? It's
What
so
the
simple. There's no right. There's no complicated. All they had to do here was find some matrix that well this connection to the hypercube, I guess, is kind of cool. But they just had to realize that these eigenvalues are bound within these first half eigenvalues, but they're all the same, and they're all positive, and they're all root n, which means that first eigenvalue is also within that bound, which is root n, which gives you what you need, which is pretty cool. If
That's
you ask
nutty.
me. Yeah.
Yeah,
The proof itself is literally 2 pages long, which is really cool. There's some comments on here about how this is actually, I think this is tight, apparently. I don't actually know. I didn't read too much detail.
Wait,
yeah.
can you explain what's the difference between AN and AH again?
Yeah, sorry. So H is your subgraph, right, that you're considering of your hypercube. So AH is the principal submatrix that corresponds to that subgraph, right? So you just take the rows and columns that correspond to the vertices in H and get rid of all the other rows and columns.
So AN corresponds to all of the hypercube then?
Yeah.
Okay.
Yeah, so AH is just the submatrix of AN. I guess that's it. Does anyone have any questions? Any other questions?
Wait, can you scroll back to the beginning really fast? I didn't get that really top. Just want to see that again, just to make full circle.
You mean this part, the sensitivity itself?
Or the one below that.
The conjecture? Or this part?
The one where you got from your result, delta is bigger than root n to the answer.
Yeah, that's this theorem, and yeah.
Okay.
Wait, so the prior result was that the block sensitivity is less than or equal to the degree of f squared. Like that was the result, not the 2 times.
No,
That
no, they pulled a fast one on me there by mentioning the 2 times one first, then being like, oh, and they improved this to get rid of the 2, and I was like, okay, well,
Wait, I mean,
thanks.
someone else improved it. That's why it was mentioned.
Yeah, but like that caught my eye first, so I was like, oh, I guess it's 2, and then I was like, where did the 2 go in the equality? And I was like, in the inequality, and I was like,
Also, right at the end, you missed a lambda because you just wrote an is equal to square root of n, but it's actually lambda. But anyway,
I must fix this typo. Where is it?
Yes, right at the end. Yeah, right there. You put an is equal to square root of n, but it's actually the eigenvalues are.
Oh yeah.
Oh,
I don't know. That's a little.
I hate Karthik so much.
What?
But
You freaking.
Why you gotta do him like that,
You did
Karthik?
everything else great. I wanted to let you know. God
while
damn.
we're fixing,
That's fine.
can you scroll up to the what's the name of the
really
theorem?
pointing out typos
Interlace?
now.
The interlace, you didn't.
Jeez. Wait, where?
I think it was the. It's like it was where you did theorem colon and then the name of the theorem colon. That seems a little excessive. You could have just written Gaussman's less lineal theorem and only had 1 colon there, which I think would have been more efficient.
You realize this is everyone is seeing this. The entire world that watches.
I'm okay with that. I think it's a
theory thing. Recorded lectures.
I think that's an
I'll cut it
important
down,
point to
don't
make
worry.
for all the people who are
I'm
watching.
just gonna
this
post
lecture.
it just exactly like this.
No, yeah, that's
People
good.
are gonna realize we have so much fun doing theory and come to the next one.
People are going to realize that you aren't using efficient notation, and that
Now is as good time as any to announce that Aditya, you're gonna give a lecture soon, right?
Okay, I'm busy this weekend. Maybe I'll do 2 weeks from now.
What are you giving a
Okay,
lecture on,
well,
Aditya?
Hold on, let me just end the
I
recording.
haven't fully.
Oh, yeah.
decided. I think I'm gonna do.
Yeah, that's really impressive.
Hey, thanks for watching, guys.
Yes,
Like, comment,
thanks.
subscribe.
Smash that like button.
Ring
And
that bell.
I'll see you next time.